Okay, so problem 16. A gas is confined to a 0.47 meter diameter cylinder by a piston on which rests a weight. The mass of the piston and weight together is 150 kilograms. The local acceleration of gravity is 9.813 meters per second squared, and atmospheric pressure is 101.57 kilopascals. A. What is the force in newtons exerted on the gas by the atmosphere, the piston, and the weight, assuming no friction between the piston and cylinder? Part B. What is the pressure of the gas in kilopascals? Part C. If the gas in the cylinder is heated, it expands, pushing the piston and weight upward. If the piston and weight are raised 0.83 meters, what is the work done by the gas in kilojoules? What is the change in potential energy of the piston and weight? So this is the same problem as what we did earlier, except in explicitly SI units. So instead of pounds mass, we got kilograms. Instead of feet, we got meters, which is nice. So the solution should be the same as number 15. We'll go ahead and summarize our givens, list some assumptions, and go from there. So givens, we got a few equations that we can write. Zoom out. So gas is confined in that diameter cylinder. So we got a diameter of a cylinder, d underscore, there we go, cross-sectional area of the piston, and that equals 0.47 meters. We got the mass of the piston and weight. So mass underscore of the piston weight equals 150 kilograms, and gravity acceleration is 9.813 meters per second squared, and atmospheric pressure is equal to, what was it, 1 atm? Oh, they just gave it to us, 101.57 kilopascals, which is equal to 101,570 pascals. What is the force in newtons exerted on the gas by the atmosphere, the piston, and weight, assuming no friction between the piston and cylinder? Okay, so to calculate the total force upon the gas by atmospheric pressure pressing on the piston. Let's see. Well, we'll just write it out. Another one of our simple equations. Okay, so the force total acting on the piston is equal to the sum of several forces. First force that's listed in the prompt is atmosphere, so force of the atmosphere. Next force is force of the piston, and next force is that of the weight. Okay. So part A is to find this total force. We're given the weight of the piston and, well, the mass of the piston and weight, and we're given gravitational acceleration, so we should be able to find the force of that. So let's do that. So let's calculate using the mass of the piston and weight. We can at least get that. Well, let's go in order. Force from the atmospheric pressure. So force acts on an area, or pressure acting on an area is a force. So let's go calculate F ATM. This can be done by using the fact that pressure acting across an area results in a force. For the piston, this is a downward force acting along with the force of gravity. Downward force. Let's go put that. Okay. I'm not going to get fancy with vectors as in physics because this is not asking for that kind of thing. Force of gravity. Okay. So let's just list an equation then. FATM is equal to a pressure times an area. What is the area? The area is the cross-sectional area of the piston, and the pressure is the atmospheric pressure. Okay, well that leaves us asking what is, we're given P sub ATM, but what is the area cross-sectional? So calculate area cross-sectional. Because this is TechMax, we can just copy that, calculate that, great. Area of a piston, which I'm assuming is circular, is pi times the radius squared radius of the piston and we're just going to go ahead and acknowledge that the diameter, the cross-sectional of the piston, divided by 2 is the radius. Make it a little more explicit. And we're given the diameter cross-sectional area of the piston, so we should be able to come up with an area. So it's pi times some number divided by 2. Is there a hotkey to go to full screen? Let's see, fit screen width. Control 9 it says. Control 9. Oh, that's handy. So, what is that? We have 47 meters being the diameter. We'll go ahead and calculate that out. That should, and then to be more explicit, I'll list out the units as something separate. This is probably not necessary in this case, but sometimes it comes in handy. Alright, go to our calculator. Pi times 0.47 divided by 2 squared. I'm getting 0.73, nope, 0.173494454 meters. Okay, which is, we'll just round that to 5 decimal places because reasons. We can round down later. So that is the area, cross-sectional area of the piston. And so now we can plug in, let's put a label on this one, equation 260 here. So let's see, that's meta shift bang, make a label, we'll call this problem 16, area piston, area CS piston, all lowercase. Now plug in equation meta shift x or question mark problem 16 area CS piston into equation. So we're plugging equation 260 into equation 254, which you need a label for. So that's meta shift bang. This will be F problem 16, FATM. The equation, meta shift question mark. Problem 16, met FATM. Yeah, so plug in equation 260 into equation 254. All right, now let's go ahead and insert several equations. We can just copy equation 254. We'll have to delete the number reference because it's going to be, well, we can leave it, I guess, but the label has to go. Yeah, okay, FATM equals P8. So we got values for both. Pressure ATM we were given, and I'm just going to use the pascals because I like pascals. Let's go in here, do that, give that a number. That's not right. There's supposed to be an area squared, isn't it? Oh, right. When we took the meter out of that value, that becomes meter squared. There we go. You get that right? Yeah. Okay. Yeah, okay. So we got meters squared. Oh, and that is actually totally wrong. This is supposed to be a division, not multiplication. There. Pressure acting over an area. Luckily, it's relatively easy to fix that. Alright, and we just copy this, or cut this, convert this to a fraction, add that there, maybe convert this into a parenthesis. We don't even need that for parenthesis. Let's go ahead and delete the parenthesis. Let's go ahead and pull the numbers out into their own separate thing. So we got pascals per meter squared. Pascal per meter squared. Oops. And let's add in a conversion factor. So it's pretty much the same thing. Then the conversion factor is going to be Pam's kg, if I recall correctly from earlier problems. Pascal meter second squared, kilograms. So that's the same thing as saying 1 Pascal is equal to a kilogram per meter per second. No, a kilogram per meter per second squared. Yeah. And I can do this in Wolfram Alpha later maybe to confirm it, but I'm pretty sure that's the case. So we cancel out Pascals. Let's see, so that gets rid of Pascals. We get kilograms, meters, and square seconds. And this all should turn into a force, actually. So maybe this is not what we want. Yeah, let's not do this. Let's go with Pascal. Don't convert into that. Let's go into newtons. So for every Pascal, we get a newton per meter squared. Is that right? Yeah, so 1 Pascal is equal to a newton acting over a meter squared. So Pascal will be on the opposite of newtons. Yeah, that'll work. Okay, so we're getting rid of Pascals, we're going into newtons. The answer actually should be in all newtons, shouldn't it? That meter squared should cancel out. I'm missing something, aren't I? Pressure of an area is a force. Hmm. One Pascal is equal to 1 Newton per meter 1 meter squared. Is that right? Yeah, should be. If you say 1 is equal to, it'll be a Newton per Pascal meter. Something is wrong here. The units just don't line up. Okay, let's see. What am I missing? Go back to the chapter on pressure. Pressure. Yeah, force over an area is a pressure. Oh, okay. Maybe I was right. Yeah, pressure times an area is force. Okay. Dang. How'd I... Guess I got that one right. Second guess myself. I guess it should make sense. The more area you have, the more force you'll have. Bring the parentheses back then. And all these equations can go away. Let's pull the units out then. Okay, let's put in our conversion factor. That gets rid of everything, and now it's everything should be in newtons. Plug that into our calculator. $101,570 times 0.17349. That gives me 17,621. 3793 newtons. Let's keep that as is. We can do sig figs later. Right. So we got a force ATM. That's one of the three. Now we need force of piston and weight. Both will come together. Now that. Calculate. So we're the sum of these two forces equal the gravitational force acting upon mass, the mass of the piston and weight, since we are given this mass as m piston weight, the value for that is may be calculated as, and then we'll go ahead and add in a little thing here, a list of equations. That is equal to mass of the piston and weight. Is that how I wrote it? Mass, piston, and weight? Yeah, and it's that, 150 kilograms. Times G, which we already have a value for G. We're given it in the problem, 9.813. 9.813 meters per second. Let's add numbers to everything here. So that should give us a force in newtons. Since we're already in SI units, it'll just be straight newtons. All right. So 150 times 9.813. We'll put the units over here. So we got kilograms times meter second squared. We'll just take that, copy it, add in conversion factor, which is, yeah, for every newton, we have a kilogram meter per second squared. And so to make that look less, make that workable, we'll rearrange the terms. There, that's the same. Now we can get rid of this middle parenthesis and start eliminating stuff. So kilograms cancel, seconds squared cancel, meters cancel. We should just be left with newtons. And putting this into my calculator, 150 times 9.813 gives 1471.95. 1471.95 newtons. That is equal to the combined force of the piston and weight, or the weight of the piston and the weight. Oops. So now that we have F piston, F weight, and F atmosphere, we can add them all together. Now that F piston, F weight, let's keep them in order. Nope. F ATM are known or are calculated. Now that we have values for those three variables, F total may be calculated using an equation. F total, we had one up here, 253. Let's add a meta shift bang. Problem 16, F total. Do we have? Yeah. Problem 16, F total. Meta shift question mark. Problem 16, F total. All right. Total force, several equations. F total, where are we? 253 it was, yeah. Let's just copy some of this stuff. Okay. F underscore text total. Don't give that a number because it's already up there. FATM, so we have a number plus a number plus a number. FATM was this number, so we'll just put that into the first one. F piston and weight are actually together, so we'll just go like that. And that should be it. We just plug these numbers in together. 17,621.3793 plus 1,471.95. That equals 19,093.3293. Okay. We can add in a comma tab. Shall be in newtons, and that is the total force acting upon the cross-sectional area of the piston that is in turn pressing down on the gas. And if the whole thing is static, then that also corresponds to the absolute pressure of the gas. Okay, so do we get part number A? What is the force in newtons exerted on the gas of atmosphere? Yep, that is it. So answer of part A answer. Part A answer. The total force pressing down on the gas is, and I'll just write it out, 19,093. Let's see, let's go ahead and just round that. What's the sig figs we got? The piston seems to be the lowest one, only 2 sig figs. So we'll just put approximately 19,000 newtons. Let's go ahead and bold that so we can find this answer later. All right, now for part B, we want, what is the pressure of the gas in kPa? So it's definitely going to be an absolute pressure, but it's just kind of the reverse of the thing. Pressure is force acting over an area. Across an area relative to force. Yeah, that's it. All right. In order to, with regards to part B, the pressure of the gas can be calculated by dividing, well, let's see, dividing the force pressing against an area. Dividing the total force acting upon the gas over a how should I word this? The pressure of the gas is equal to, it can be calculated by taking an area in contact with the gas, calculating the force acting upon the gas through that area, and dividing it by the area. In other words, we can just explain it in an equation. So the pressure, and this will be the absolute pressure of the gas, is going to be the force total acting over an area. So in this example, one force and corresponding, let's see, is the total force acting upon the gas divided by the corresponding area over which the force acts. That's a better way to put it. In this example, the pressure is the absolute pressure of the gas is equal to the total force acting through the piston's cross-sectional area F total divided by the same cross-sectional area. In other words, we get this CS piston. Okay, and then we'll just go ahead and plug in values for this. So force total, we have that. Area CS of the piston. Did we calculate that separately? We did. I don't think in the previous problem we did, but we did this time. All right. And that will be, yeah, 19. Be the same number, except we're going to pull out those units. Okay, and add in a conversion factor. conversion factor is going to be the same one we used, which is for every Newton. Actually, we're going to go to pascals, don't we? Yeah. So every pascal, we have a Newton per meter squared. And just because we can, that simplifies into Pascal Newton meter squared. Alright, and everything cancels. Meters cancel, newtons cancel. And we're left with pascals. Put this into my calculator. 19,093.3293 divided by 0.17349. That equals 101,054.3507 pascals. And that is the pressure of the gas. Pressure of the gas. Okay, and is that what we were asked for? Yep. Oh, and kPa. So let's go ahead and do one more conversion. Let's do that one more, but let's do it up here. Pascals. Let's go ahead and do that. For every 1,000 pascals, we get a kPa, kilopascal. So 1,000 goes into the number thing. We got kilopascals. So that should be the same, except we get a 1,000 figure down here. And all that really should change is that we get this. Let's go ahead and just round that to 110 kilopascals. Let's see, part B answer. The pressure, the absolute pressure of the gas is 110 kilopascals. Make that a bold one. All right, part B done. Part C. Part C question was, if the gas in the cylinder is heated, it expands, pushing the piston weight upward. If the piston and weight are raised 0.83 meters, what is the work done by the gas in kilojoules? What is the change in potential energy of the piston and weight? So 0.83 meters is, so a gas being heated and being raised. Yes, that is work because we have a force acting across a distance. The force in question is the force across the piston. That force is the force total we calculated earlier. And so the work is just that force times the distance of how much it was raised, 0.83 meters. And the change in potential energy is kind of a separate question. That's just the height that is raised, because we're assuming it's being raised vertically upward. That's just the height gain. So mgh, or the mass times gravitational acceleration times the change in elevation. So that's going to be a separate equation. But let's take this 0.83. Let's see, add that to the givens here. So let's go with a delta H or Z. I guess it wouldn't be fancy. Nah, let's go with height. Let's go with Z then. Fine. 0.83 meters is the height that it is raised. You know what? I'm the boss here. Delta H. Okay. Now to answer part C. Since the gas is heated, and so the problem doesn't actually assume, it doesn't say the pressure inside the gas changes, it just that it's raised. Well, actually, that doesn't matter, because if the force is constant, because the piston and the weight and the atmospheric pressure outside isn't changing, the pressure of the gas will change, but that doesn't change the work done, because the work is just a function of F total. Okay, oh, that's a cool concept. The work performed by the gas is equal to the force against which it expands multiplied by the distance the displacement caused by the expansion. Also, the change in potential energy of the piston and weight is equal to the, that's it, may be calculated by, well, let's see, change in potential energy is a function of the change in elevation, the gravitational field strength, and the mass of the piston and weight. Okay. The work may be calculated by multiplying, well, let's just add in there, the work performed by the gas is equal to the force against which it expands, and we'll put in parentheses F total multiplied by the displacement caused by the expansion, and then we'll put in parentheses delta H. Put delta H in there, or do we put delta Z? Yeah, delta H. Okay. Work may be calculated like so, and we'll put in a list of equations, mathematics, several equations. Work is equal to force times distance, and the distance we're talking about is actually the delta H. The force we're talking about is total. Then it's just plug and chug, I guess. So force total, we already calculated that, is that value. 0.83, I think, meters was the displacement of the piston. Yeah, 0.83 meters. Okay. So yeah, and I got this lovely number times 8.3 times Newton times meters. That will be joules. So for every Newton meter, you get a joule. So equal that number times joules. And that equals, let's see, 19,093.3293 times 0.83 meters. 15,847. Dot 46332 joules. That's the work done. Now, change in potential energy of the piston and weight may be calculated like so. So the change in potential energy is equal to mg delta H. And this is the mass of the piston and weight, which I think we already have a value for that. Yep, 150 kilograms. Times G, which we already have. That's... Do I already use that somewhere? Yeah, we already did. Okay. Well, there's G. Times 0.83 meters. So these units will be 150 times 9.813 times 0.83. And that will be kilogram meter squared per second squared, and that is equal to a joule. Yeah. Yeah, pretty much the same thing. All right, so 150 times 9.813 times 0.83 equals 1,221.7185 joules. That is equal to delta U. All right, so part C answer. The work performed by the gas is approximately, what are our significant figures here? 0.83, it's only 2 sig figs. Approximately 16,000 joules. Change in potential energy of the piston and weight is approximately 1,200 joules. Part C answer, let's bold that. All right, so that's that. But what about the reverse? So you have the gas acting on a distance, but what about the force? Atmosphere acting against the gas going out. Is there any reversible thing? I don't think so. I think that would just make the problem too complicated. Okay, work performed by the gas is 16,000 joules, 1,200 joules, great. I'll go ahead and zoom out. Got a lovely solution there. I'll go ahead and export that to PDF, to the repository. All right, staged. That was chapter 1, problem 16. Add solution. Go ahead and push that to the repository. There, it's been pushed. Okay, that is that. Now for the next stream.